So why don't we start with a brief discussion again about what's going to happen next week when we return to physical classes. A lot of you wanted to stay on Zoom. Some of you wanted to come back to physical classes. A few of you suggested that some other faculty had been doing both at the same time, Zoom and physical classes. And after talking with some colleagues, that seems like the best of both worlds. So what I'm going to try to do starting on Monday is have this Zoom lecture at the same time on the same Zoom channel without any changes, except that it will be, I will be giving the lecture from the regularly scheduled classroom for the course, which you can find on the course website, instead of from my home. So you're welcome to come to that classroom and see the lecture in person. You're welcome to watch it over Zoom live. And in fact, one of the things that I really like about doing these things on Zoom, even though there are other disadvantages, is that this chat window gives me the opportunity to get some live feedback from you on the lecture questions without feeling like you're interrupting me. And so I wanted to preserve that possibility as well. So that's the plan. And I will see those of you in person who want to come to the in-person lecture on Monday. And otherwise, I will see you on Zoom, or otherwise, as before, you can watch it in the recorded format. So I think everyone wins this way. There may be some small disadvantages, like because I'm going to wear a mask, the lecture audio might be a little less clear, but we'll see about that. Okay, so we've seen applications of path problems in scheduling, and we've seen them in transportation, routing, planning. How do you get from here to there kinds of questions. And I wanted to tell you about a kind of different application of path problems for voting today. The specific path problem that we'll be looking at is the widest path. And really, most of this lecture is going to be about voting. So we'll get through the widest path part fairly quickly. It's pretty easy. So let's do that first. The widest path problem is the input is just like a shortest path problem. You have a graph. It can be a directed graph. It can be an undirected graph. You have weights on the edges. They're just numbers. You might want to assume that they're all positive, but you don't have to. The difference is, how do we measure the quality of a path? And what we're going to measure it by is the bottleneck of the path, the minimum weight of any of its path edges. We've seen this already in the minimum spanning tree problem. So the weight of this red path from A to D, A, B, C, D, is 6. It has 3 edges, 10, 6, and 9. You take the minimum of those 3 edges. That is the weight of the path. It's a very different measure than adding up these numbers. Just take the smallest of them, and that's the widest path problem. So in this example, there are actually 4 different paths from A to D. You could go, there's a typo here. This should be A, B, D. You can go A, B, D, 10 and 4, the minimum is 4. You can go A, B, C, D. We've already seen that path. The minimum is 6. You can go along the bottom, A, C, D, 5 and 9, the minimum is 5. And you can go A, C, B, D, zigzagging the other way, and the minimum is 4. So of these 4 different paths, they have these 4 different numbers. Well, 3 different numbers, 2 of them are the same. That's not unusual. You're going to get a lot of numbers the same on these paths because typically there can be exponentially many paths, but there's only a linear number of different edge weights that could be the minimum. So there's going to be a lot of repetition. But question on the chat, is final the only time when attendance is mandatory? Yes. The final will be physical unless you have some exception through disabled student services, which I will of course be honoring, but other than that, attendance is mandatory at the final. So what we want is the path that maximizes this minimum weight. It's in the shortest path problem, we're trying to minimize something. In the longest path problem, we're trying to maximize something. And here we're trying to maximize something. So it's closer to a longest path problem than a shortest path problem. There's an equivalent version of this problem where you negate all of the numbers and you measure the quality of a path by the maximum weight, and you try to make that maximum weight small. That's also useful sometimes, but today we'll be looking at the widest path problem, which is the one here. And we already saw this problem in the undirected case because we were looking at a problem of finding paths between computers in a computer network that maximized the bandwidth of the path. That bandwidth is exactly this number, the minimum bandwidth on any individual connection along a path. And we saw that the tree that maximizes the bandwidth between all pairs of vertices is the maximum spanning tree. So in the undirected graph case, we actually already know how to solve this problem, but I want to look at the directed case. So as I said, undirected widest path, we already know how to do the maximum spanning tree. We want the widest path. And that's not the only algorithm for the undirected case. So a natural special case that you might keep in mind is one where you have a specific start and a specific destination, and you want to find the widest path between those two vertices. One thing you can do in that case is look at the median among all the edges in your graph, in an undirected graph. This algorithm only works for undirected graphs. Now, if there is a path that only uses edges that are heavier than that median edge, then you know that whatever the widest path might be, it's also going to be heavier than that median edge because it's even heavier than the paths that we found. So if the source is connected to the destination among this subgraph of only the heavy edges in the graph, then there's no point in even keeping the lighter edges. We can throw them all away and get a recursive subproblem with half as many edges. We've made a lot of progress. On the other hand, maybe it's not true that the source can reach the destination using only heavy edges. The heavy edges are useful, but they don't get you all the way there. You have a lot of different components in this graph of the heavy edges. Well, if that's true, you can collapse each of those components into a single vertex and make a smaller graph that way that again doesn't have half the edges that it had before. All of the heavy edges are now gone after this collapse, and recursively find the path connecting these components in the remaining graph. So this gives you an algorithm whose running time is linear to get rid of half the edges, plus m/2 to repeat in the smaller graph, plus m/4 plus et cetera, which is a geometric series adding to linear. So we don't know how to do minimum spanning trees or maximum spanning trees in linear time deterministically. But if we have a single source, single destination, widest path problem, we can solve that problem in linear time. It's an easier problem. In the directed case, we can essentially use Dijkstra's algorithm. The only thing is Dijkstra's algorithm is maintaining a priority queue of vertices by the priority of the best path that we've seen so far to that vertex. And all we have to do is change what we mean by the best path to that vertex to use this widest path quality measure instead of the sum of the lengths quality measure. So this is true for a lot of different graph problems that you can optimize as long as these problems have the property that the optimal path to any vertex is composed of an optimal path to the second to last vertex plus one more edge. As long as that second to last path must also be optimal, then you can use Dijkstra. You just have to change your definition of the priority, the quality of the path that you have found to each vertex. And so here we're using as the priority the length of the final edge on that path. And if you use that as your priority in the relaxed step of Dijkstra's algorithm, and then when you're pulling vertices out of this queue, always pull the vertex whose priority is the largest number. That'll give you the widest path in a directed graph. If you apply exactly this algorithm to an undirected graph, then what you have is Yarnik's algorithm. We've already seen this algorithm in the undirected case, but it also works for directed graphs. And again, it's not the best known algorithm. So there is a faster algorithm for directed single source, single destination graphs. It has this kind of nasty looking time bound m log star n. Log star is how high this tower of powers of 2 needs to be greater than or equal to n. So it's a more slowly growing function than log. It's a more slowly growing function of log log. It's a more slowly growing function than log log log, etc. But it's actually a much more quickly growing function than the inverse Ackermann function we saw before in the minimum spanning tree algorithm. So there's a whole zoo of these slowly growing functions. This is one of them. I'm not going to go into the details of this algorithm. You should know that faster algorithms exist, but I'm not going to test you on the details of what is this log star function. Now, the version that we're going to need for the voting problem is the all pairs widest path problem. That means that for every pair of vertices, we need to find the widest path from one vertex to another. This is the same problem that in the shortest path problem we saw using Johnson's algorithm. We can repeatedly call Dijkstra's algorithm, but in the shortest path case, we need to make all of the edge weights non-negative first. And we use one round of Bellman-Ford to do that before we switch to Johnson's algorithm, to Dijkstra's algorithm. For the widest path problem, just like in undirected Yarnik's algorithm for minimum spanning trees, the positive negative edge weight thing isn't important anymore. So in the widest path problem, we can just always use Dijkstra's algorithm without any extra effort. But there's an extra trick that we can do to make the all pairs directed widest path problem faster. If we just use Dijkstra's algorithm with a binary heap, we would get an mn log n time for the total running time. If we used a Fibonacci heap, we would get mn plus n squared log n for the running time, because we're doing n copies of Dijkstra's algorithm, one for each starting vertex. There's a different kind of priority queue that we can use. If we know that all of the priorities are just small integers, numbers from 1 to m, then there's a way of just using arrays as a priority queue. It's called a bucket queue. I don't want to go into the details because I have too much other stuff to cover today. That will let you run Dijkstra's algorithm in linear time based on the assumption that all of the priorities are really small integers, small enough that you can index an array using them, and just put the items with different priorities into different array cells and search for the first non-empty array cell to find your minimum priority item. So I don't want to assume that the graph starts out having very small integers as its priorities, but you can convert it to one that does just by sorting, and then replace all of the priorities by their positions in this sorted order. That doesn't affect the order of comparison between any two priorities, and so you get the same paths as the result. And then once you've got the paths, you have to convert them back to the numeric priorities that you started with. And so this idea of pre-sorting and then using a priority queue that is specialized to integer priorities lets you run the modified Dijkstra in linear time for each instance of the Dijkstra's algorithm. Mn total plus n log n for sorting. If you use a comparison sort, gives you Mn. So this algorithm is, it's the same running time as Bellman forward. It's not perfect, but it's fast enough for the voting application, because in that application, n is actually going to be pretty small. If you have a large graph with a large number of edges, there are also theoretical improvements to this. If the number of edges is like n squared, well, the most it could be is n times n minus 1, but quadratic in the number of vertices. Then this algorithm is going to take O of n cubed time, which in the voting application is okay. That time is not really an issue, but maybe for some other application, you might want to run this on really large graphs for which n cubed is too slow. There is a theoretical improvement based on turning this into a linear algebra problem and using fast matrix multiplication algorithms. The fastest known time bound to multiply two n by n matrices is something like n to the 2.34. And somehow when you use that algorithm as part of a widest path algorithm, and again, I'm not going to go into the details of this, that 0.34 part of the exponent doubles, so that what you get is n to the 2.68. It's faster than n cubed. It's a lot more complicated. I don't know of any situation where you would really want to use it, but it is a theoretical improvement. And if we could improve the time bound for matrix multiplication, there's no real known reason why it couldn't be as fast as n squared to multiply two matrices. We just don't know an algorithm that fast. So that's a big open problem in theoretical computer science. Any improvement in the running time for fast matrix multiplication would also improve this time bound for the widest path problem. Okay, so that's really all I want to tell you about widest paths. It's a different way of prioritizing paths. If you change Dijkstra's algorithm to use that priority instead of the length of the path, you get an algorithm for finding these things. You can run it for each starting vertex and find all pairs, which is what we're going to need in the method that uses widest paths for voting. Before I talk about that method, I just wanted to give you an overview of just what is the problem here? What are we trying to achieve in a voting system? So this is all about elections that have more than two candidates, because in a two-candidate election, what you want to do is more or less obvious. Choose whoever is the majority winner among those two candidates. There isn't really any other reasonable choice. But when you have three candidates or four candidates, the choices between them, depending on the voter priorities, the voter preferences, can be a lot less obvious. And how you want to weight those priorities and preferences is also not obvious. So The assumption I'm going to make going into here is that all of the voters in an election, everyone who gets to vote in an election, goes into the election having some preferences in mind among which candidates they like and which candidates they don't like. And I'm going to make a fairly strong assumption here, which is that those preferences can be described by a permutation of the candidates. They can strictly order the candidates. They like this one first, this one next, this one next, this one next. There are weaker assumptions you can make, but this makes the problem simpler. So every voter has a permutation on all of the candidates saying exactly which one they like first, which one they like second, which one they like third among them. And if we can collect all of this information from all the voters, or get them to specify parts of that information in a sequence of votes, as we do in most elections, you know, in many elections, we don't allow the voters to tell the voting system what their preference order is. We just ask them to pick one. But that is giving the election information about each voter. And what we want to know is who wins. Which candidate is going to be the one declared to be the winner of the election. There are different rules that we can use to take this information and turn it into a winner, and we need to have that winner specified in advance so that we don't, you know, have a situation after the election that's just as confused as the one before the election, where all of the candidates think that they individually won. That would not be a good outcome. So we need to not have any disagreement about what the voting system is. And we need an algorithm that can take this input, a preference ordering of the candidates for each voter, and different permutations on a set of C candidates. And it's usually reasonable to assume that N is much bigger than C, into a single output, a single winning candidate. Or maybe you want to actually order the candidates for some, I mean, political elections, typically a single person wins, but some other situations you might want an ordering. So in fact, here's a situation where you do want an ordering. And in fact, it's a situation where the voters and the candidates are kind of reversed. There's a lot of candidates and a small number of voters. Let's think about a sporting event that has maybe 100 competitors entering at the start of the event. And so those are the candidates, but the event consists of multiple stages. You can think of it as like a pentathlon or a biathlon or a decathlon, where the competitors all compete in more than one sport, and you have to somehow combine their results from each of these different sports. Now, if one of these sports is a long jump and you have to measure how far they jumped, another of these sports is a race and you have to measure how quickly they raced, it seems kind of arbitrary to set just a conversion factor to produce a number that you can add for each of those results of an individual event. Instead, what I would like to do is to think of each of the events that the athlete is participating in, the long jump event or the sprint event. Each of those events is a voter. And when the athletes all participate in that event, they get a ranking from that event. That ranking is the preference ordering of that voter. The long jump event prefers the athlete who jumped the longest. The sprint event prefers the athlete who ran the fastest, etc. So there's a small number of voters, each of the events that they participated in, a larger number of candidates, each of the athletes that's participating in this combined sporting event. And what you want to do is to produce a single output ranking of how well each athlete did in that combined sporting event. So it's again, pretty much exactly the same situation, except that these numbers are turned around so that N is small and C is large. The algorithms that we'll be looking at don't really care about that distinction. They can be used for either kind of problem. A simplifying assumption that I'm going to make that really you do have to think about is I don't want to assume that there's any ties. I don't want to assume that there's any ties in the individual preference orderings of the candidates. I don't want to assume that there's any ties in the number of voters that voted for one person versus another. I don't want to assume that there's any ties in the output ranking. That's something that you have to deal with even in the two candidate election, because if you have an election with two candidates and some number of voters, it's entirely possible that the voters are exactly equally split between those two candidates. And maybe you have to toss a coin or something like that to resolve the tie. But for today, we're just going to assume that doesn't happen. We don't have to deal with it. Now, I'm going to go through some standard election systems. And the one that we most often use in US elections is a plurality vote. That means that the only information we get from each voter is their first place choice, the first element of their permutation. And we assign the winner to be whoever gets the most first place votes. I mean, it's a clear rule. You know who won. You can look at the numbers very quickly and see who won. So it has that going for it. It's not the only possibility, and we'll see as we go that there are many other choices. But it is a widely used rule. In the US, we often use it in the form of a runoff election. So in June, we'll have an election between many candidates, among whom the two who have the most first place votes then go on to a second election in September or November, where the candidate with the majority wins. Now, if you're going to do a runoff election like that, that's a different system. It's not a pure plurality vote would not have the runoff. It would just have first place votes for all the candidates. If you're doing a runoff election like this, then actually you can do it all at once. If you just make each voter specify their permutation among all the candidates, then you can simulate, once you have that information, if that information is given to you as what the voters tell you at the election time, then you can use that permutation information to tell which two candidates get the most first place votes in the primary. And then you can use that same information to tell among those two winners of the primary, which one has the most voters preferring that winner over the other one. So you can use the permutations to predict how each voter would vote in a second election without having to hold that second election separately. And that leads to the idea of an instant runoff or single transferable vote election. It is a widely used voting system. It's been used for over 100 years in Australia for their elections. It's been used for the Academy Awards for over 10 years. And it's starting to come into use in the US. I wrote these slides. I've revised them for today's lecture, but I wrote them a year or two ago for an earlier instance of this class when Maine was in the news for US elections. Today, this morning, Alaska is in the news because they're also switching to this same system, the instant runoff single transferable vote system. So today's lecture is very topical. It's about an item that is on the front page of today's newspaper. So this system, everybody votes by specifying their permutation, their preference for the candidates. And it works best if the number of candidates is relatively small. So the Alaska system that we're talking about today actually is a little bit of a hybrid system of this runoff election plus single transferable vote, because the new Alaska system will have a primary where as many candidates as want to enter, and you take the top 4 first place votes from that primary and go on to the second election in November with those 4 candidates. But then among those 4 candidates, you use this single transferable vote system. So you go into an election like the ones that'll be held in Alaska with 4 candidates. You go into the Academy Awards with 5 or 9 or some other number of nominees for an award. A small number, small enough that you can ask all the voters to write down all of their preferences for who should be first, second, third, fourth, and fifth out of this slate of nominees. And then, so you have more than one nominee for an award, more than one candidate for an office that can only be held by one person. So you have to do something to reduce that number of candidates. And what you do is go into a loop. The loop is going to get rid of one candidate each time through, so you do it until there's nobody left. What you're going to do is look at these preferences that each voter has and compare them against the remaining candidates, the ones that have not been eliminated. So every voter is going to have some favorite among the remaining candidates. They might not be their favorite candidate overall, but their favorite candidate overall might have been eliminated earlier. In that case, you move on to their new favorite, the favorite among the candidates who are still alive. And you just count for each candidate how many voters chose that candidate as their favorite. But you don't use that number to choose a winner, you use it to choose a loser. So you're going to eliminate the candidate who got the fewest favorites, the candidate who was the favorite of the smallest number of voters in this count of favorites among just the remaining candidates. So even though some people have been eliminated and maybe their voters moved on to other candidates, now your candidate still, even after collecting support of other people, they still don't have enough votes. You eliminate them. Now, the number of voters for whom, if you have a particular candidate, the number of voters that choose that candidate as their favorite only goes up as this election progresses, as we eliminate other candidates. Because once a voter has chosen somebody as their favorite, they're not going to have to choose again until that favorite is eliminated. And so while a candidate is still alive, their number of favorites keeps growing and growing. And so if you ever get to a situation where somebody is the favorite candidate of more than half the voters that are left, then there's no point in keeping on going around and around and eliminating the remaining candidates. You're going to get that candidate as the winner and you might as well stop. So there's an early stopping condition, but this is really the main idea of the algorithm. Just loop through, figure out who's the favorite among the remaining candidates, and get rid of the candidate who has the least support, that measured that way. It's not the only system that uses preferences. And so one of our professors at UC Irvine, Don Sari, has a joint appointment in mathematics and sociology, I believe, is an expert on many things, including the motion of planets around stars. But one of the things he's an expert on and has written a book on is voting systems. And his favorite system is this one. It's called the Borda Count, and it is also a widely used system. You've probably encountered situations where you use it. They do use it in some national elections in small countries. And it's really just a point system. So if you have 5 candidates, then as a voter, each voter can give 4 points to their first choice candidate, 3 points to their second choice candidate, 2 points for their third choice candidate, 1 point for their fourth choice candidate, and 0 points for their last choice candidate. So more points for being the first place choice of a voter, fewer points for being later down in the ordering. One less point at each step. So if there are 4 candidates, you get 3 points for first, 2 points for second, 1 point for third for each voter. So every voter gives away points using this formula, and you just count up the points, and the candidate with the most points wins. No repeated rounds, nothing, just add up the numbers. Very simple system. So I've given an example here of just some numbers. And I chose these numbers carefully to show you that it's actually possible for all 3 of these systems to give you different results, even in a 3-way election. So if the voter preferences are like this, where 11% of the voters, maybe there's 1,000 voters and 110 of them, have the priority ordering: A is first, B is second, C is third. A much larger percentage, 24%, like the numbers A, C, B, et cetera, in the percentages shown here, and you can check that they add up to 100. If we just compute a plurality vote, the plurality means you count up first place votes. These 2 blocks of voters go to A, these 2 blocks of voters go to B, these 2 blocks of voters go to C. You get 35%, 11 plus 24, 33%, and 32%. The winner is A. A has the larger number of first place votes. If you do the Borda count, where these voters give 2 points to A, 1 point to B, these give 2 points to A, 1 point to C, etc. And you count up how many points everybody gets, then the formula is over here. A gets 96 points, B gets 97 points, and C actually gets 107 points. Lots of people like C. And you can see that because among the second place choices, when a voter prefers A first or prefers B first, those voters tend to prefer C over A or C over B very strongly. So that's why C gets such a high number in the Borda count. If we do this as an instant runoff election, because C has the smallest number of plurality votes, C is the first candidate to be eliminated. After C is eliminated, the voters for C get spread out among A and B. So these voters, the ones who like CAB, get redistributed as A voters. They can no longer choose C as their favorite. C has been eliminated, so they choose A as their favorite. These voters, the ones who have the priority ordering CBA, choose B as their new favorite. And when you count that up, a lot more of the C voters switched to B than switched to A. And so B ends up winning the instant runoff election. You have to choose your voting system before you do the election, because if you tried to choose a voting system after the election, A, B, and C would all get to argue, well, under this normally commonly used voting system, I would win, therefore I should win. This is why it needs to be specified ahead of time, because if it's specified ahead of time, you can't make that argument. It's just everyone agrees going into the election that we are making the election this way. But we still do need to choose. And one way that we might think that we can choose is to axiomatically choose, figure out what axioms, what properties we want our voting system to obey. And then let's make sure that our system has those properties. So a natural property that I think these systems do have actually, a candidate, maybe not the Borda Count, a candidate with the majority of first place votes should win, maybe. Or here's a weak version of that. Suppose that a candidate gets all of the first place votes, then it seems pretty clear they should win, right? There's a symmetry condition that we definitely want to obey in a democratic system, that all of the voters are treated equally, that nobody gets special treatment over others. That's not actually true in US presidential elections, because the number of presidential electors per state is not a uniform fraction of the population of the state. So voters in large states from like California get treated a little differently in US national presidential elections than voters in small states. It doesn't obey the symmetry property. But there's a weaker symmetry property that we might want to have, which is that at least everybody's vote is heard. There's no single dictator. The one voting system that you might imagine, for instance, for making decisions about this class. I made a decision about how we're going to do online versus Zoom lectures. I asked for your opinions, but then there is a super voter, me, and my preference is the one that we use to actually decide the matter. So in this sense, for that kind of decision for this class, I'm the dictator. You can have an opinion and I might listen to it, but ultimately my opinion is the one that's going to be used for the elections. And you could imagine an election system that's like that. We pick some person in the system that is holding the elections. That person judges who the winner is, and nobody else's vote counts. That would obey the weak majority property, but it would not be a very symmetric system. Finally, this third property is a little weird. We don't want a spoiler candidate. And what I mean by that is, suppose some candidate in an election X, sorry, in some particular election, candidate X enters the election, and because of the preferences of the voters in that election, X does not win. X is not, maybe not even there to win. But because X was part of the election, they affected the outcome among the remaining candidates, in the sense that if the same election was held without X there, you would get a different outcome. That makes X be a spoiler in some sense, that someone who is there in the election for the purpose of changing the results rather than for the purpose of winning. And that's usually considered a bad thing, although it's less obviously bad than the majority and symmetry property violations would be. Now, there's a famous impossibility theorem that says, even with this very weak majority and weak symmetry systems, it's impossible to avoid spoilers. There is no election system that can guarantee all three of those properties: weak majority, weak symmetry, and no spoilers. This was proved in around 1951 by Kenneth Arrow, who won the Nobel Prize for it. So very famous result. We can't get a perfect election system, one that has all of the properties that we might desire. And it's actually pretty easy to come up with examples that show why it's not possible. Here's another. Is this actually the same system of voters? It's slightly different. It's another system of numbers for preferences for voters. Where if you look at just the head-to-head comparisons, the two-way comparisons, they have these outcomes. A is going to beat B if they had a two-way election head-to-head without C present. B is going to beat C, and C is going to beat A. There's this kind of cyclic ordering that this graph of who beats whom is not a directed acyclic graph. And because of that, we have this idea of a spoiler that no matter what voting system we use and no matter what person this voting system chooses as the winner, somebody else can be seen as the spoiler. So if A wins, for instance, if A wins, then B is a spoiler candidate because B did not win in a scenario where A is the winner of whatever election system we choose. B did not win. But if B weren't there, then we would have just C and A against each other and C would win. So the presence of B as a non-winner caused A to win instead of C, and therefore B is a spoiler candidate. And that's true regardless of which of the three candidates we pick. So with this cyclic ordering of the head-to-head candidates, that essentially already proves Arrow's theorem that avoiding spoilers is impossible. Okay, in just a couple minutes left, let's bring this back to widest paths. So if we can't avoid spoilers, then maybe we can get a weaker property. And the weaker property we would like is that if a candidate wins every head-to-head comparison, if you had just an election between two candidates and you counted how many people prefer one versus the other based on the permutations that we know for each voter, we can simulate what would happen in each two-candidate election. And if one candidate wins every head-to-head comparison, then according to the Condorcet property, that candidate should win the whole election. That is a weaker version of the no spoiler property, because if the no spoiler property is true, then this has to be true as well. And the first system of votes that I gave you does have a Condorcet winner in which candidate C beats both A and B head-to-head and therefore is the Condorcet winner. The second example had the cyclic output of head-to-head comparisons and did not have a Condorcet winner. So the Condorcet property tells you that the first election should be won by C. The second election is still up in the air. So there's this system called the Schulze method for widest paths. And the Schulze method is you count the votes in each head-to-head comparison. So if A gets 47% and B gets 53% of the votes in a head-to-head between A and B, then you make an arrow from A to B with that number, 47, the percent of the vote for A. You make an arrow from B to A with that number, 53, the percent of the vote from B to A. Here's the same graph for the second example of votes. Now, take this graph and compute all pairs widest paths and relabel the edges on this graph by those widest path numbers. So I've changed this 47. The 47 up here is the number of voters who prefer A to B. I've changed it to 49 down here because there's a wider path from A to B. ACB has width 49 instead of 47. So A would beat C head-to-head, or A head-to-head against C would get 49% of the votes. C head-to-head against B would get 56% of the votes. And so somehow transitively A to B gets 49%, even though really they only get 47%. So these numbers are just all pairs' widest paths. Now, the key theorem that I'm not going to prove for you because I don't have time is that in these numbers, if you use these numbers instead of these numbers, if you use the widest path widths instead of the actual head-to-head votes, then there is always a candidate who wins all the head-to-head pairings. In this case, C beats A 53-49. C beats B 56-49, wins both of those head-to-head comparisons, and is the winner. And it's the same as the Condorcet winner in this case. But in this case, when there was no head-to-head winner on all comparisons in the original votes, when you change those numbers to be the widest path widths, you get A as the winner. A beats B 55-51 instead of 55-45, but A beats C 55-51 instead of 49-51. A only got 49% of the vote head-to-head against C, but there's this much wider path, 55-57, giving A a 55-51 edge in the comparison of widest path widths. So that's the Schulze method. Find all pairs' widest paths, use those numbers to perform head-to-head comparisons, pick the head-to-head winner, and there always is one unless there's a tie. So we can prove that if there's a Condorcet winner, this method will find it. Question on the chat, is instant runoff inefficient compared to standard elections? It's a little slower, but the speed is not really an issue because the time is a function of the number of candidates, which is really small. So we're not really looking at running time here. We're just looking at the mathematical properties of these voting systems. And for the widest path method, those properties include always finding a Condorcet winner. When there is one, the harder property to prove is that there always is a winner. And this slide gives you an argument for that, but I don't have time to go over it. So there are some elections that use this widest path method. It's used by some technical organizations more than it is in national and international elections. And I think maybe because it's somehow a more nerdy system, the biggest reason not to use this system is it's really hard to explain to non-technically educated voters what is going on. What does it even mean? But it works well. It has some really nice mathematical properties that the other ones don't. So widest paths can be computed efficiently. They're as easy as shortest paths, often easier. Comment on chat, even hard for the CS students. There is an impossibility theorem saying there's no election system that can completely eliminate spoiler candidates, but widest paths can be used to make a system that has a weaker no spoiler property, the Condorcet property. And that's not true of the common alternatives. But really, this is a social issue rather than a technical issue of which one you want to use. You have to persuade people that the election makes sense and that it's a system that they buy into. So I will stop there, a little bit over time.